Here, we're going to investigate some basic principles of projectile motion using basketball. There are a number of elements involved, several of which are easily measured and also a few which can be easily calculated. The value which we are going to solve for is initial velocity. With the origin placed at the point of launch and our measured time, distance, and launch angle values, we can calculate an initial velocity for the basketball just as it leaves my hands. Here we have our range, which is 42 feet, or about 12.8 meters, the time of flight, 1.75 seconds, and the launch angle, 52 degrees. It is also important to point out that the launch height is about 8 feet, or 2.44 meters, while the final height, the height of the basket, is 10 feet, or 3.05 meters. Here's the kinematic equation which serves us best in this instance based on our known variables. Remember, while there is often more than one kinematic equation which can be used to solve for a given variable, there is usually one which is easier to apply. Okay, so after using our kinematic equation to solve for initial velocity, our result is about 11.34 meters per second. Here, we're going to investigate basic kinematics on an inclined plane using a skateboard from rest. There are a few primary determining factors such as the initial velocity, the force of gravity, and the angle at which the plane is inclined. Ultimately, after calculating the final velocity from point A to point B, we're going to compare these experimental results with the theoretical equivalents to get a general idea of how much otherwise unaccounted for factors such as friction and air resistance have affected velocity. The result of comparing the theoretical data to the experimental data is that experimentally, the sum of the forces was greater than that of the theoretical, which is why the experimental final velocity of 5.98 meters per second was slightly greater than that of the theoretical at 5.73 meters per second. This is likely due to an additional positive wind force, which was enough to not only offset any friction, but increase experimental acceleration and velocity slightly beyond the theoretical. It is interesting to point out that there are two sources of kinetic friction, that which exists between the wheels and the pavement, and also that which exists between the wheels and the axles upon which they rotate. Here I've done a small experiment to test the measured number of revolutions per minute of this record as it rotates on a record player. The record player is designed to spin the record at 45 revolutions per minute. However, because the record fails to play properly, the sound is distorted. My hypothesis is that the record player is spinning too slowly at a rate less than 45 revolutions per minute. For the purpose of this experiment, the angular acceleration is 0 because the angular velocity is constant. Also, the spot with the stamp marks the maximum radius on the record. In a given amount of time, this portion of the mass travels a greater linear distance than any other spot on the record with a smaller radius. So here are the results. I have timed 45 revolutions 3 times. Using this data, I have calculated the revolutions per minute and the angular velocity. These results go against my hypothesis that the record was spinning too slowly. The results suggest that on average, the record player spins the record about 3.4% faster than the required revolutions per minute. Using a pool table, I'm going to demonstrate how momentum and kinetic energy can be transferred from one object to another. As I generate force within my body to strike the cue ball, I initiate a chain reaction. Both momentum and kinetic energy is transferred from me to the stick, to the cue ball, and eventually to the entire rack of balls at the other end of the pool table. Elastic collisions are instances in which no kinetic energy or momentum is lost. These type of collisions are virtually non-existent in the macroscopic world. The type of collisions which we are observing are inelastic collisions, where kinetic energy is transferred, however, it is eventually converted into some other form of energy. This diagram shows the path of the cue ball before the collision and the path of both the cue ball and the 8-ball after the collision. The cue ball transfers both kinetic energy and momentum to the 8-ball. Their linear momentum can be expressed both as a scalar quantity and also as a vector.